Hello everybody, hope everybody is doing great. CRS here. In this video, we will be talking about what impulse is and what its implications are. An impulse is something that changes the momentum of the body. You all know from Newton's first law that if there is a body moving with a certain velocity, it continues to move with that velocity forever unless it is acted upon by another force. Now, if you just look at for how long this force acts and how it changes its momentum, this change in momentum that the force causes in a certain duration of time is what is known as impulse. Now, let's look at what it means mathematically. We have Newton's second law. Newton's second law tells us that the rate of change of momentum is directly proportional to the force. You can write that as F being proportional to dp by dt. In order to make it an equation, you can simply write F equal to dp by dt. The proportionality constant becomes 1. You want to write it in vector form, certainly you can add that arrow. From this equation, you can get here, which is dp equal to F of t into dp. It simply tells you that force is a function of time. Force depends on time. You can either have a constant force or it could be a time dependent force. To integrate this, you integrate it from P1 to P2, which is initial momentum to final momentum. That gives you the total change in momentum. That total change in momentum is what you call impulse J, right? On the right side remains the same. It's an integral of T1 to T2 f of t dt. Now, this quantity is what you call impulse, and in very simple words, you can say that impulse is defined as the total change in momentum. You see, integral of t1 to t2 of f of t dt gives you impulse, which is essentially change in momentum. With this mathematical understanding of impulse, we can go further to look at how to apply this newly gained knowledge in different numericals. Let's look at a question now. A ball of mass m moving with a velocity v naught collides with a wall. After impact, it rebounds with the velocity v naught by 2. So there is a ball that hits the wall with a speed v naught and then goes to this side after getting bounced off from the wall with a velocity v naught by 2. That means the velocity of rebound is not the same, it has slowed down. That means the velocity has changed. There is an impulse. It received an impulse from the wall, because of which it now has a different momentum. So let us write down the same scenario with respect to its momentum and its impulse. This is exactly like the free body diagram. Let's give it a try. We have the wall here. That is the wall. The ball is initially heading in this direction. The ball is heading in this direction. The velocity is v naught, my dear friends. This velocity can be resolved along the x and y axis. The question says that the x axis is towards right and y axis, the positive y for this question, is in the downward direction. So both of these velocities are now positive. If you talk about the ball's momentum, then the mass of the ball is m, so its initial momentum is mv naught. The x-axis makes an angle of 37 degree with the initial momentum, so I shall draw that angle to be 37 degree. The momentum mv naught can now be resolved along coordinate axis. We have mv naught cos 37 degree along the positive x and mv naught sin 37 degree along the positive y. And the ball bounces. It goes this way and then it bounces. Here, I'll just, right now it's bouncing. I'll keep it here so that you can see what are the impulses that are acting on it. Let me say that there is an impulse due to the wall in that direction. The ball, if you just look at it, traveling only along the x-axis, of course it's traveling along both x and y. I'm just talking about the ball traveling along the x-axis. So it goes, the wall hits the ball, and then it changes its direction, starts moving this way. So the ball received an impulse in this direction. Let me call it J1. That's J1. And this J1 is along negative x direction. We will incorporate the direction while we write the equation. Also, do you see that the final momentum in the downward direction has also changed? I can prove that to you. Let me find out what is the final momentum in the y direction. We figured, and also along the x direction, the ball comes, hits the wall, and comes to this place, and what it possesses is final momentum. Now the ball is going this way, the ball is moving this way. You can resolve its momentum along the coordinate axis. The direction of its movement along the y-axis has remained the same. Before it was going down, before collision it was going down, after collision also it's still going down. But along the x-axis, the ball was moving towards positive x. After collision, the ball is now moving along negative x. The angle it makes with the x-axis after collision is 53 degree. That's given in the question. So we will write that as 53 degree. The momentum here is mv naught divided by 2. That's the momentum now. This can again be resolved as mv naught divided by 2 cos of 53 degree along the x-axis. This momentum is negative, which is along the negative x-axis. We will write that in the equation. And then the momentum along the positive y direction is mv naught divided by 2 sine 53 degree. Sine 53 degree is 4 by 5. 4 by 5 makes it 4 divided by, after multiplying with 2, it becomes 10. 4 by 10 is 0.4. And here cos 37 is, let's say, cos 37 is going to be 4 by 5 again. And here sine 37 is 3 by 5. 3 by 5 is 0.6. 0.6 mv naught was in the downward direction. After being hit by the wall, the momentum becomes 0.4. Momentum becomes 0.4. That means the momentum has decreased. Before it was going fast in this direction. Now after hitting the wall, it's going down. That means it received an impulse in the upward direction. The ball was going with a high velocity. It received an impulse, and then it's now going with a lower velocity. That means the ball must have received an impulse in that direction. So I'll call that impulse J2. With all of these momenta resolved, we can now write the equation, which is essentially impulse momentum theorem. Quite easy to do that. Listen to me carefully and try to follow it. I have a momentum along the positive x direction, so I shall write this momentum along the x-axis, along the x-axis. All right. We have the initial momentum mv naught cos 37 degree, and then it receives an impulse in the negative x direction, because positive x is that way, negative x is this direction. So minus j1, because again negative x, that is equal to the final momentum. Initial momentum plus the impulse should give you the final momentum. The final momentum is mv naught by 2 cos 53 degree, but that momentum is along negative x-axis, so I shall put that with a negative sign. We have mv naught divided by 2 into cos 53 degree. It's time we find what impulse J1 is. So m v naught cos 37 is 4 divided by 5 minus j1 becomes equal to minus m v naught into cos 53 is 3 by 5. So we have 3 divided by, you have 5 into 2 makes it 10. Well, you can calculate J1 now. J1, dear friends, becomes equal to 4mv naught divided by 5 minus 3, maybe plus, because this goes to this side, this comes here, mv naught, 3mv naught divided by 10. This can certainly be calculated further. So you have 6 plus, I think we have 8 mv naught divided by 10 plus 3 mv naught divided by 10, making it 11 mv naught divided by 10. Now that's the impulse J1 to begin with. That's the impulse J1 to begin with. So, well, having said this, we can similarly write it along the positive y direction. I mean, along the y direction, along the y direction. Along the y direction, we have the ball moving in the positive y direction initially. So you can write that as m v naught sine 37 degree, sine 37 degree, and then it receives an impulse in the upward direction. So that's negative y minus j2 I shall write, because that's negative y, equal to, now the ball is still going down, so the momentum is still positive, and it is m v naught divided by 2 sine 53 degree, sine 53 degree. Having said this, we have m v naught sine 37 degree is 3 divided by 5, my dear friends, minus j2 equal to sine 53 is 4 by 5. So we have 4 mv naught divided by 10. Well, what does J2 become equal to? J2 becomes equal to 6 mv naught divided by 10, because I just multiplied and divided by 2 so that the denominators become the same, minus 4 mv naught divided by 10. Answer you have for J2 is 2 mv naught divided by 10, which is equal to J2 being equal to mv naught divided by 5. That's the answer for J2. So the ball receives impulses in these directions. So the total impulse would be in that direction, and that's J. It would be the vector sum of both of these. So it would be root of J1 square plus J2 square. But the question only asks me to calculate the components. So we have calculated the components. This is the X component of impulse, and that is the Y component of impulse. Now that's how you apply impulse momentum theorem and get the impulse for bodies. Going further, hoping that this question has taught us how to deal with impulses, we shall go further to the next question. This is an interesting question. A 300 kg space probe. So the mass of the space probe is 300 kg. Is moving in gravity-free space at a constant velocity of 300 meter per second. So I have a rocket here. The rocket is moving with a constant velocity, let's say uy. It's moving along the y-axis, so I shall write it as uy with a speed of 300 meter per second. All right. To change its direction, the space probe's rockets have been fired in a direction perpendicular to the direction of initial velocity. So the rocket fires the thrusters on its side, because of which the rocket starts to turn. The rocket starts to turn, and maybe the thrusters are at the top. Let's say it's here. The thrusters are here, and the rocket starts to turn. And when that is the situation, let's say that this is the thrust. I shall write it as thrust, right? The exhaust gases come this way, so the rocket experiences a force in that direction, because of which the rocket would start turning towards right. For the thrust of 4000 newtons, so the force acting along the x direction, because it's perpendicular to the direction of initial velocity, is 4000 newton for 225 seconds. 225 seconds. Okay, neglecting the mass of the fuel fired, calculate the angle turned by the rocket. Initially, the rocket is now moving along the x direction, so it makes an angle of 0 degree with the y-axis. We will have to figure out by what angle does the rocket turn. Let's try to figure this out. The impulse received by the rocket can now be calculated. The impulse is only going to be in the x direction, and this impulse ends up changing the velocity of the rocket. Let's find out what's the impulse in the x direction. Impulse in the x direction is force multiplied by time. Force is 4000 multiplied by time is 225, and that makes it 90,000. Newton second is the SI unit of the impulse. So 90,000 Newton second is the impulse received by the rocket in a direction perpendicular to the initial velocity. So that's in the x direction, because of which the momentum along the x direction will change. There is no component of the impulse in the y direction, because of which the momentum in the y direction does not change. Having understood that, the initial momentum along the x direction, dear friends, is 0. The reason being, the rocket is only moving along the y direction, not along the x direction. So the momentum is 0 along the x direction. Going further, we can calculate what is the final momentum after receiving the impulse. The initial momentum is 0, and then it experiences an impulse in this direction, jx, which is 90,000 in this case, and this gives it its final momentum along the x direction. That's m into vx. I told you that the initial momentum and the final momentum along the y direction would remain the same. So uy is also equal to vy, which means that velocity along the y direction would remain the same, because of which the momentum remains the same. We have jx, that's 90,000. That's equal to m. M is the mass of the rocket now. That's 300 kg, and it's moving with a velocity vx. We will have to figure that out. I will have to figure that out. Well, all you have here is two zeros going away, and velocity along the x direction now is 300 meter per second, which is the same as the velocity along the y direction. That means the total, the rocket now, if you just imagine this to be the rocket now, that's your y-axis and here is your x-axis. The velocity along y-axis is 300 meter per second, and the velocity along the x-axis also is 300 meter per second, which simply means the resultant velocity will be along the angle bisector. Whenever you have two vectors which are equal in magnitude but act at different directions, the resultant vector always will be an angle bisector. So the angle bisector would simply mean that this angle is 45 degree. The resultant velocity is v. That means if you just multiply mass on all places, then the diagram here becomes a vector diagram for momentum, and the final momentum is in that direction. Do you see that the rocket was initially, before these rockets were fired, it was going along the y-axis, but after it received an impulse, The rocket now is going in that direction, because total velocity is the velocity that you have to take into account, not just x or y. The total velocity makes an angle of 45 degree, which means the momentum also makes an angle of 45 degree. Because of this, the new direction of the rocket is at 45 degree with the y-axis. So the rocket, during this time, 225 seconds, the rocket has turned by an angle of 45 degree. So this is an interesting question. This is exactly how different maneuvers are done in space in order to correct the trajectory of an already launched space probe. Having said that, let's look at the next question. A right angled wedge of mass m and base angle theta rests over a smooth horizontal surface. Let's try and answer this question. Question being a little large, let's keep it at one side. With a velocity v naught and collides with a small ball of mass small m moving horizontally with a velocity v naught collides with a wedge on the sloping surface. If after collision the ball starts moving in vertically upward direction, then calculate number one, the impulse of the normal reaction applied on the ball by the wedge. We have to calculate the impulse of the normal reaction. Let's try and understand the question. I have a wedge here. Now that's a wedge. Okay. So here we have a wedge. And then I have a ball. The ball is heading towards the wedge horizontally. So let me just say it's moving with a velocity u. The question says, or maybe the question very clearly says that it is, v naught. So let me say that it is v naught. V naught is the velocity with which it's moving towards the wedge. The question also says that the angle of the wedge is theta. The angle of the wedge is theta. And after collision with the wedge, the ball starts moving in the upward direction. The ball starts moving in the upward direction. Let me call that velocity v. What is the impulse of the normal reaction applied on the ball by the wedge? That's the question. So let's draw the impulse diagram for the ball when it is colliding. Let me draw out the wedge once again so that things become very clear. Okay. This is when the ball is colliding. The ball is right now colliding. I can keep the ball here, it's colliding, but then I just want to separate them out and see what's happening during collision. The ball will receive an impulse in a direction perpendicular to that of the plane of the wedge, because that's where the direction of normal reaction is. You can calculate, call that J1. J1 is the impulse due to the normal reaction. Because of Newton's third law, the same impulse the wedge would experience in this direction. So let me call that J1. It's all Newton's third law. This is exactly what we have to find. Okay. Having understood this angle is theta. You can resolve these vectors into the x and y components. If this angle is theta, then this angle also is theta. J1 is the impulse. Okay. All right. Everything moves. Fine. No problem. J1 is the impulse. I shall write J1 here. And then you have J1 sine theta in this direction and J1 cos theta in this direction. Well, the same thing holds for the colliding ball. This diagram is during collision, right? This is not before or after. This diagram is for during collision time. It's all Newton's third law. So, well, this angle is theta. J1 cos theta is in the upward direction and J1 sin theta is in the horizontal direction. So these are the set of impulses that are acting on the ball and the wedge during collision. Well, if you just look at it, the ball was moving along the horizontal. It hit the wedge and then it stopped moving along the horizontal. It's only moving along the vertical now. It came, hit the wedge, and then it's moving along the vertical. So it's not moving along the horizontal at all. That means the impulse, the horizontal component of the impulse given by the wedge was exactly equal to the momentum of the ball in that direction, and they cancelled out and the ball stopped moving along the x direction. But then the wedge's normal reaction gave it an upward impulse as well, because of which the ball started moving in the upward direction. And that's how this question is to be understood. Having explained to you that, let's continue and write down the equations for what we just said. For the x-axis, you see, the ball was initially moving along the negative x direction, let's say. So that's minus m v naught. It was moving along negative x. We will assume that this is x-axis and that's y-axis. So the ball was moving along negative x, and then it received an impulse in the positive x direction. So I shall call this plus j1 sine theta. Do you see? J1 sine theta is in the positive x direction, and then it stopped moving along the horizontal. It only moved along the vertical. So along the x-axis it is 0. So this is along the x-axis, right? You can calculate what is J1 now. J1 is the impulse due to the normal reaction. J1 is the impulse due to the normal reaction, and that's equal to mv naught divided by sine theta. I'm sorry. So this is the impulse due to the normal reaction. I think we've answered that question. All right, the next question to you is impulse of the normal reaction applied by the ground on the wedge. Oh, if you just look at this particular wedge, I shall move the wedge here just to show you what's happening with the wedge. Move it a little up. Well, let's find out what's happening with the wedge. The angle is certainly theta. We'll write that here. The wedge is sitting on the ground. The ground is quite tough. So the wedge receives an impulse in this direction. The normal reaction is in that direction. Look at this. The normal reaction is in this direction. J1 sine theta is the impulse that the wedge receives towards negative x-axis, but there is a J1 cos theta that's trying to push it down, but then the floor is really hard to let it go into the floor. So the floor gives an exactly equal normal reaction. So let me call that J2 in that direction to stop the wedge from going down. So this normal reaction that the wedge receives is also impulsive. Having told you that, you can calculate what is J2, because the question is calculate the impulse of the normal reaction applied by the ground on the wedge. So J2 is the normal reaction from the ground on the wedge. So let's write down what's J2. J2 is the J2 is the impulse, and that exactly cancels out J1 cos theta. So you can write J1 cos theta out here. They cancel out, and that's why there is no change in velocity I along the y-axis for the wedge, right? Okay, now we know what is J1. J2 can be easily figured out. J1 is mv naught divided by sine theta. That's into cos theta, because the cos theta is in here, and the answer you should get as an extension to this is mv naught cot theta. That is the impulse. That is the impulse. Well, that's one part of the question. Let's go further and find out what else does the question ask us to do. So Push it to this side, making some space. Okay. All right. We are through with this part. What is the velocity of the ball after collision? That's the next question we've got to answer. What's the velocity of the ball after collision? The ball is now moving in the upward direction because of this impulse, J1 cos theta. Before it collided with the wedge, it was not moving along the y direction. So, along the y direction, along the y direction, y axis, for the ball, initially it was not moving along the y axis, so its momentum is 0 along the y axis. Now it receives an impulse in the positive y direction. Do you see? Positive y direction. So plus j1 cos theta is its impulse, and because of which it starts moving in the upward direction with a velocity v. So the mass is m, and I shall write that v. Okay. So which simply means that the velocity with which it would be traveling can be obtained by substituting j1, and j1, my dear friends, is mv naught divided by sine theta, and there is a cos theta here. It's equal to mv. M gets cancelled, so velocity with which it would go up is equal to v naught cot theta. So that's the answer to the third question. That's the answer to the third question. Let's go and answer the last question now. The last question is, what is the velocity of the wedge after collision? Now we are talking about the wedge. The wedge has to move this way. Let me call this velocity Vw. That means velocity of the wedge. The velocity of the wedge depends on how hard the ball has hit the wedge. Do you see that the impulse received by the wedge in the horizontal direction is j1 sine theta? It's j1 sine theta. Before this, the wedge wasn't moving. The wedge wasn't moving. And then it receives an impulse in the negative x direction. So you can write minus j1 sine theta. It receives an impulse. That's the only impulse that is acting on the wedge in the horizontal direction. And that makes it move. M is the mass of the wedge, and then it moves with a velocity Vw. J1 has been found some time ago, so you can write, of course it moves in the negative x direction, so I have to put the negative sign there. So we have minus J1 being mv naught divided by sine theta multiplied by sine theta equal to minus mvw. I have minus getting cancelled and sine theta getting cancelled. So the velocity of the wedge directly from conservation of momentum is mv naught divided by capital M. This is the velocity of the wedge. So such problems are quite common in JEE. NEET exam can also come up with a subset of this, but then if you can understand and solve this question repeatedly, it will serve you with a lot of skill, and you will be able to tackle the exams in a much better manner. I'll be back with another video, and let's learn together. Remember, the day you stop growing is the day you start decaying. Thank you so much.